Okay, the next section is section 14.2, categories of sound waves. There are three main categories of sound waves: audible waves, infrasonic waves, and ultrasonic waves. The audible waves are longitudinal waves that lie within the range of sensitivity of the human ear, approximately 20 to 20,000 hertz, or commonly referred to as 20 kilohertz. Infrasonic waves are longitudinal waves with frequencies below the audible range. Earthquake waves are an example. Another example is submarine communications. Since radio frequency waves don't travel very far underwater, submarines communicate underwater by using extremely low frequency, or ELF, waves. They're in the range of 3 to 300 hertz. Ultrasonic waves are longitudinal waves with frequencies above the audible range for humans and are produced by certain types of whistles. Animals such as dogs can hear the waves emitted by these whistles, since their hearing range is a lot higher than humans. You can also produce them with piezoelectric effect, which we'll discuss next. Ultrasonic waves are sound waves with frequencies greater than 20 kilohertz. These sound waves can be used to produce images because of their higher frequency and corresponding short wavelengths. Ultrasound is very commonly used in medical applications, both as a diagnostic tool and in certain treatments. For example, ultrasound can be used to image internal organs. Ultrasonic waves are much safer than X-rays, but their images don't always have as much detail. But certain organs, such as the liver and the spleen, are invisible to X-rays, but can be imaged with ultrasonic waves. Medical workers can measure the speed of the blood flow in the body with a device called an ultrasonic flow meter, which makes use of the Doppler effect. This is something we'll discuss a little later. The flow speed is found by comparing the frequency of the waves scattered by the flowing blood with the incident frequency. This figure illustrates the technique that produces ultrasonic waves for clinical use. Electrical contacts are made to the opposite faces of a crystal, for example, quartz or strontium titanate. If an alternating voltage of high frequency is applied to these contacts, the crystal vibrates at the same frequency as the applied voltage, emitting a beam of ultrasonic waves. This method of transforming electrical energy into mechanical energy, called the piezoelectric effect, is reversible. That is, if some external source causes the crystal to vibrate, an alternating voltage is produced across it. A single crystal can be used both to generate and receive ultrasonic waves. The primary physical principle that makes ultrasound imaging possible is that a sound wave is partially reflected whenever it is incident on a boundary between two materials having different densities. If a sound wave is traveling in a material of density rho sub I and strikes a material of density rho sub T, the percentage of the incident sound wave intensity reflected, PR, is given by the equation shown here. For this equation, we assume that the direction of the incident sound wave is perpendicular to the boundary and that the speed of sound is approximately the same in the two materials, which is pretty true for the human body. If it doesn't strike the material in perpendicular, it'll just be scattered away from the transducer. We used to use the ultrasonic imaging to look for rebar in concrete, or to look for cracks in the rebar. These were methods that were developed at Southwest Research for what we call non-destructive testing, NDT, or non-destructive evaluation, NDE.